Hello everyone, this is Dr. Webb, and in this calculus video we are going to be talking about higher order derivatives and what these can tell us about the shape of functions, the shape of the graphs of functions. So at this point we're pretty familiar with starting off with a function and then taking its derivative, and we get a new function, f prime of x, which tells us about the slope of f of x, tells us about how f of x is changing at each point. And, usually if we start off with, a pretty normal function, the derivative also looks like a pretty normal function. Like if we start off with a polynomial, we take its derivative, we get another polynomial. If we start off with the trig function, take its derivative, we end up with another trig function. If we start off with an exponential function, take its derivative, we get another exponential function. And so then natural question is, what happens if you take the derivative again? So if you take the derivative again, you're getting the derivative of the derivative, and we're going to call that the second derivative. So f double prime of x is the second derivative. And there's a bunch of other notation that's used. So if we're talking about the function itself, we'll usually talk about f double prime of x. This other notation is usually used for saying take the second derivative or take two derivatives of a function. And so sort of the idea of this is that d dx, d over dx, this is often called the derivative operator. And so it's a function, it's saying take the derivative of this thing, f of x. And so if we want to do it twice, you would say squared means do it twice, and then sort of applying that turns into d squared over dx squared. That's saying do the derivative operator twice on this guy, f of x. Okay, so let's think about sort of famous common example that involves thinking how to think about second derivatives. So let's let s of t represent the distance traveled at time t for something like a car or train, spaceship, something like that. Then if we take the derivative of distance traveled, that's going to give us the velocity. And so the velocity is the rate of change in the distance traveled per change in time. This is something we're pretty familiar with. And then if we take the derivative of this again, so the second derivative of distance traveled is going to be the derivative of velocity. And so this is going to be telling us about the rate of change of the velocity, the rate and change in speed per the change in time. And that's more commonly known as the acceleration. So if s of t is our distance function, then the first derivative is velocity, and the second derivative is telling us about the acceleration. This should be a of t, not a of x. Okay, so the second derivative is telling us about the rate of change of the derivative. And so since the derivative is telling us about the rate and change of the function, that means the derivative is the rate of change of the rate of change. So it's telling us about how the rate of change is changing itself. So that's a bit of a mouthful. So let's try and parse this through and think about it a little bit more precisely. Okay, so first let's focus on the first derivative and think about what its value tells us. Okay, so first of all, if the value of the first derivative is positive, so this is saying that as you move to the right, the function has positive slope. So the slope of the function is positive as you move to the right. And so what does that tell us about the function? Well, it means that the function is increasing as you move to the right. So positive first derivative means the function's increasing. On the other hand, if the first derivative is negative, that means that the slope of the function is negative. And so the slope of the function is pointing down. And if the slope of the function is pointing down, that means that as we move to the right, the function is decreasing. So negative first derivative, that means something is decreasing. Lastly, What if the derivative is equal to 0 at a point? Well, that means that the function is horizontal there, and so it's neither increasing or decreasing. So having derivative equal to 0, that's sort of in between, it's just going flat at that point. Okay, so now let's move on and think about the second derivative. So if the second derivative is positive, this means that whatever the value of the derivative is, the value of the derivative is increasing. So the slope of the function is increasing, so the slopes are getting bigger, and so the function is curving upwards. So if the slope is going higher, that means that the function is curving upwards. On the other hand, if the slope of if the second derivative is negative, that means that the first derivative is decreasing. And so the slope of the function is decreasing. And if the slope of the function is decreasing, that means the function has to be turning downwards or curving downwards. Okay, and so if the second derivative is positive and the function is curving upwards, we often call this concave up for curving upwards. If the second derivative is negative, we'll say that the function is concave down. And that means that it's curving downwards. Okay, and so the second derivative, we're going to say it tells us about the concavity of the function. Positive second derivative, as we said before, means concave up. Negative second derivative means concave down. So concave up, curving upwards, up like a cup. Second derivative negative means concave down, down like a frown. Okay, so let's try and link knowing what the first derivative and the second derivative are into what the shape of a function is. Right? So first we have that the first derivative is positive, and so this means the function is increasing. And the second derivative is positive as well. So it's increasing and concave up. Right? So this means the whole way across, the slopes are going to be positive, but as we move from left to right, the slopes are going to be getting higher and higher. So let's just sort of start off with some points. Let's put a point here, and we know the slope, we want the slope to be positive here, and maybe we'll put another point here, and since we move farther to the right, the slope is not only still positive, but it's more positive than before. And so if we try and connect these dots, we get the general idea of this is what a function that is increasing and concave up looks like. All the way across, we pick any point. As we move over, the slopes are getting a little bit higher. Okay, and so this is an increasing and concave up curve. It's kind of curving, it's starting up, going up, and as you go up, it's getting steeper and steeper. Okay, so now we have the first derivative is negative, and the second derivative is positive. And so this is a decreasing and concave up. Okay, so if it's decreasing but concave up, that means that at the beginning, the slope must be pretty negative. So at the beginning, the slope must be very negative. But then as time goes on, that slope flattens out. Okay, and so this is a decreasing concave up curve. Right? And if we take these tangent lines, the slope there is very negative, but as we move further over, it has flattened out. And so at the end, it's still a little bit negative, but not nearly as negative as it was at the beginning. Okay, now what if the function is now, the first derivative is positive, so it's increasing but now the second derivative is negative, and so it's going to be increasing in concave down. What is this going to look like? Well, so at the beginning, if we want the slope to be positive, but then as time goes on, it's going to get less and less positive. That means at the beginning, we should have the slope be very big. But then as time goes on, it starts flattening out. And so this is an increasing in concave down curve. Okay. And so if we think about points over here, the slopes are very steep. But then as we move further and further to the right, the slopes start getting more and more towards horizontal. So they start flattening out more and more. So at the beginning, the slope is very positive, but since the second derivative is negative, those slopes are flattening out and going towards zero, or at least decreasing as we go across. Last but not least, what if we have a decreasing function that is concave down? So this means that it starts off decreasing, and as time goes on, it gets more and more decreasing. So if it starts off fairly negative, and then as time goes on, it goes on more and more negative. So this is a decreasing concave down curve. And so if we start at the beginning, it's negative, but not very negative. But then as we go further along, it's getting steeper and steeper in the negative direction. So this is a decreasing in concave down curve. And so I think it's really helpful to think about these four curves together when you're thinking about what a function is. And so it's very helpful to go and actually remember these concepts, that if you want something that is increasing in concave up, that looks like this. Increasing in concave down looks like that. Decreasing in concave up. So decreasing in concave up, that means it's very negative and flattens out. And then last but not least, decreasing in concave down, what we just have. And so then once you know these four basic curve shapes, then just by knowing what the sign of the first derivative is and the sign of the second derivative is at the same time, you actually can piece together what the curve basically looks like over its whole thing, just by looking at where the first derivative is positive and negative and where the second derivative is positive and negative. Okay, what about taking more derivatives? Of course, this is a perfectly reasonable thing to do. So if you take the derivative of the second derivative, you get f triple prime, which is the third derivative, and you can keep going from there. The derivative of the third derivative is the fourth derivative. We stop using primes usually around that point, and instead just do put what number derivative it is in parentheses up above it. And so then the derivative of the fourth derivative is the fifth derivative, and this just keeps on going forever. And a lot of functions, in fact, sort of most pretty much everyday functions you can think of, actually you can take the derivative as much as you want. Now sometimes with polynomials, what eventually is going to happen is all your derivatives start turning into zeros and stay at zero the whole way. That's perfectly fine. That doesn't happen with trig functions. Like if you take the derivative of sine, you get cosine. And so then if you take two derivatives of sine, well, that's the derivative of cosine, which is minus sine. And then if you take the third derivative of sine, well, that would be the derivative of minus sine, which is minus cosine. And then when you take the fourth derivative, you're taking the derivative of minus cosine, And the derivative of cosine is minus sine, and then give another minus sign, and you're right back at sine. And this loop starts all over again. And so for sine and cosine, taking multiple derivatives, you actually just start cycling through the same functions over and over again. So the question is, do these higher derivatives tell us more about the shape of the function? And the honest answer is really not that much. Really, we get the most information from the first and second derivative. And so that's usually where we're going to be focusing in on the information. If you know a function, its first derivative and its second derivative, that tells you an awful lot about what the function looks like. That is all for this video, and I will see you again soon.